Okay, so welcome back. This is part 3 in our series where we talk about how to write some very simple code to simulate projectiles. In this case, I've got some projectiles shooting out of a cannon, and we show you how to simulate with two very simple equations, how to simulate the motion of these under the influence of gravity so it's kind of realistic. Unlike a lot of what you might see in movies and stuff where people kind of ignore the physics and thinks it's too difficult. Well, it's not. We showed you with two simple equations how to do this in the previous videos. I encourage you to look at that. In this video, we're going to address one of the missing factors. And you can see when these objects hit the ground, they just kind of stick and slide, which is fine if you're going to hit some ice and slide, but it doesn't realistically simulate bounciness. When something hits the ground, it's going to bounce. So we're going to show you how to do some very simple code to add to this to simulate objects bouncing. Now, this is going to be a very simple approach like we did before. I know in YouTube videos people aren't interested in complex, so we're going to do the simplest approach I can think of. And we're just going to show how to simulate objects bouncing off the ground. And this is the simulation we're going to come up with. We're just going to have one object, and we're going to launch it, and you can see it's going to come down, hit the ground, and bounce up. And it's under the influence of gravity and the initial velocity, and it bounces again, and it bounces again, and it hits the wall, and you can see it bounces up and down. And up here, I'm reading out the velocity and height for every time step. Now, when you think about it, when you see this, you can see that it's got an initial velocity, hits the ground, and if you notice, it basically changes direction. So we're going to have to figure out how we can simulate that in code, and it turns out to be very simple. So as with all my videos, we're first going to think about it and plan and design before we start writing code, which unfortunately most people do. They just write code without thinking, and then they get into a mess. So we're going to think about this and plan out our code as a professional would do, and that will save us a lot of headaches later on. So, collisions. What happens when something collides with what's called a rigid body? These are rigid body collisions. You can imagine the object is coming down under the influence of gravity, it hits the rigid body, and it bounces off. So what changes? What are we going to have to simulate? What changes in this simulation as it hits the rigid body? Well, the first thing you can see, well, it's coming down in this direction towards the ground, and what it does is it changes direction, right? The big thing that happens is it changes direction. It was going in this direction towards the ground, but then it bounces and goes off in a different direction. So somehow we're going to have to figure out what's the change in direction that we can simulate, right? And you can imagine if you're, for example, if you've done any like ray tracing software, you're familiar with ray tracing, it's really not much different from that, where you simulate light hitting, for example, a mirror. It comes in at a certain angle, and if it hits a mirror, which is a specular reflective surface, if it hits a mirror, it's going to bounce off in another direction. And if you know anything about ray tracing, you know that it comes in and goes out at very similar angles. Right? So let's say it's coming in here at 45 degrees from this floor or the surface of the mirror. It's going to go out at 45 degrees. Right there, we know that we can simulate the change in direction, in this case, by just taking, using the same angle, but it's in a different direction. All right? So we're going to have to figure out what that incoming angle is so that we can flip it and send it to the outgoing direction, all right? And we know that they're going to be the same angle, but it's going to end up being the negative. It's going to be the inverse. For example, actually the incoming angle for that vector relative to this floor or this surface is going to be, say, minus 45 degrees. And we want to flip that to make it plus 45 degrees, all right? So we're going to have to figure out this angle, and then we can just negate it or flip it so that we can figure out what the outgoing angle is. Now, that's not always the case. I mean, again, we're doing a very simple thing, If the surface causes that object to bounce off at a little different angle, you're going to have to take that into account, but we're just assuming it's going to come in and go out at the same angle, all right? So we got to figure out what this incoming angle is. What else do we need to figure out? Well, the velocity coming in, the speed, the feet per second coming in, may or may not be the same as the feet per second going out. So for example, say you've got a very bouncy ball and it hits the ground, it's going to bounce back up at a very similar speed to when it hit the ground. On the other hand, if you have like a lump of clay and it hits the ground, the outgoing velocity is going to be almost zero, or it is going to be zero. So the incoming velocity might be 10 feet per second, but the outgoing is going to be zero. So depending on the object, it's going to have a different amount of bounciness. So a nice bouncy rubber ball is going to have a incoming velocity and outgoing velocity. They're about the same. So we're going to have to figure out what's the incoming velocity so we can determine, is that going to be the same or different from the outgoing velocity? So now we've got a good feel for a couple things we're going to have to figure out. We're going to have the incoming velocity, the vector. What's the magnitude and angle of this incoming velocity, so we can figure out what the outgoing velocity is, all right? So really it's not very complex for this simple situation, but we're going to have to do a little bit more calculation than we did previously. So if we go back to the previous video where we looked at just the projectile motion, we came up with these two simple equations to define the x location and y location at each point in time, at each time step in our simulation. And the x location was based on the initial velocity, and the y location was also a factor of the gravitational force or gravitational acceleration we show here. So we're still going to have to do that. However, we're going to also have to detect if the object has hit the floor, if it's going to bounce off the floor. So how are we going to do that? Well, first of all, we have to, for each simulation time step, we have to calculate the x location and the y location, right? Using these equations we did before. We also are going to want to calculate the incoming velocity vector. What is this incoming velocity, magnitude, and angle? And how are we going to do that? Well, velocity is very simple. It's feet per second. It's speed with direction. So we're going to have to figure out how many feet per second this object is coming in before it hits the ground. So how do we do that? Well, if we know its location when it hits the ground, and we know its location at the previous time step in the simulation, we can take the difference to say how many feet it has changed in that time step, divide that by the number of seconds in the time step, and that gives us feet per second. So it gives us the speed, and we can do that for the x direction and the y direction. And if we get the x velocity and the y velocity using that simple equation, then we can come up with a velocity vector with a magnitude and angle, right? So each time step, we're going to have to know what the previous location was in the previous time step and the present time step, and from that we can calculate the velocity vector, right? So we're going to have to add that to our code, calculating the velocity vector. Now, we're going to have to do a detection of collision. If the y location is at or below this floor, we're going to say, hey, we've got a collision. And we're going to have to change the velocity of the object to represent this new vector going off in another direction. So we're going to have an if the y location is at or below the floor, we're going to have to recalculate the initial conditions. And if you think about it, all we're doing is we're saying at this point where it collides, we have to reset all the values so it goes off in a different direction. And that's kind of like we're starting from zero, like we did with our initial part of the simulation. It's like we are refiring it, but now we're starting from this floor position. We're refiring it with a new angle, with a new velocity, and we can even use a new start from zero simulation time. So really, when it hits the floor, it's like we are restarting our simulation with new numbers, and we can treat our code like that, where we just basically reset the parameters and refire the projectile from this location where it hits the ground. The additional stuff, we have to calculate the incoming velocity vector and then determine if we've hit the ground. If we have hit the ground, we just refire the projectile with these new parameters, the new magnitude, direction, and start the time simulation from time zero. And we're all set to go. So that's kind of the general focus of our code that we're going to have to add collisions to these simulations. So here is the code I'm using, and I'm using C++. You can use any language you want, but I'm using C++. I'm in Visual Studio. And here I've got the method that runs when I want to simulate that single projectile bouncing on the floor. And I'm calling it void collision sim. And when I press that button that you saw before, let's go through and do it. When I press this collision button, it runs that collision sim method and does the simulation on one object and simulates the bouncing and the effects of gravity and so on. Basically, it does what we did last time. It calculates the X location and Y location every time step, and this is going to get called each time step in our program loop. It's the same equations I used before. The only difference is instead of doing a vector of 5 values for locations and firing angles and sim times, I'm only doing it for one. So I got rid of the vectors and I'm just doing single variables for the X location and Y location of our one projectile. So X location is X location initial plus initial velocity feet per second. And then the X is the cosine of the firing angle times the sim time. And then the Y is the sine of the firing angle to give you the Y component. And then we have to add the gravity effect, which we showed previously. So that hasn't changed. So as we said before, we first figure out what's the X and Y location. And then we're going to calculate the incoming velocity vector. And as we said before, we need the X and Y feet per second. And to do that, we take the present X location, subtract the previous X location, and that will tell you how many feet it has traveled in that one time step, divided by how many seconds are in that time step, and that will give you the X feet per second. So that's the X component of velocity. The Y component is identical. You take the Y location minus the previous Y location, divide by the time step seconds, and that gives you the X component of the velocity. So that's very simple. Now we've got Vx and Vy. To figure out the magnitude, you just do the square root of Vx squared plus Vy squared, and that gives you the magnitude of that velocity vector. And the angle is the arctangent of Vy over Vx. And you want to then convert that to degrees instead of radians, because that arctangent will give it to you in radians. So you multiply times 180 over pi, and that gives you the angle of this incoming vector. So now we've got a velocity vector, magnitude and angle, and we're all set. All we have to do is negate this angle and modify the magnitude to figure out what's our new projectile velocity from the point at which it hits the ground, all right? So then we do the if. If the Y location is less than the floor location, then we have to refire the projectile by reinitializing the simulation time, the initial location, the initial velocity, which depends on the bounciness. So the outgoing velocity is going to be either 1 or something less than that, depending on how bouncy the object is, and the flipped firing angle. So we're going to zero out the main simulation time, start from 0. The initial X location is going to be our present X location because we're starting from there. the initial velocity is going to be the incoming magnitude of the velocity vector. And what I did is I multiplied times 0.8. So I'm saying it's not totally bouncy, it's only 80% bouncy. So the velocity going out is going to be 80% of the incoming velocity. And then the firing angle is going to be the negative of the incoming angle, right? So now we have initialized this and we can basically refire our projectile. So up until this point, we've calculated the X and Y location in feet in real world coordinates. And what we have to do now is we have to map those values, the feet values, into pixel values and determine where to put them on the screen. Previously I did a video on this map ranges, how we convert from feet to pixel coordinates. Here I've added the pixel limits for our screen to the viewport width and the viewport height. Do that however you want. So now we have mapped it to pixel locations, and that's what the integer X location pixels. And then we can clamp it to the screen as we talked about before, which means just don't go outside the range of the screen. And then here, what I'm doing is I'm just drawing that on the screen. In my case, I'm drawing a background to fill an image object with pixels, and then I'm drawing the box on top of that at these X and Y locations in pixels. And here I'm just sending that to the GPU to print out. And then I am resetting the previous location to the present location, and I'm incrementing the simulation time. So with all of that, what we can do is we can basically hit this collision button. It runs that simulation, and based on the parameters we put in on what point is the floor, it will bounce and keep bouncing until it runs out of energy. Now again, this is a very simplified version. Actually, you might have inertia and spin of the object, and you might want to manipulate the properties of the object and the floor and do a whole bunch of fancy stuff. But again, we're trying to do something very simple for what people are looking for on YouTube. So that's kind of it for the collisions. Maybe if there's interest, we'll get into something deeper later on. But that's it for now. If you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Otherwise, take care. Have a really good day. Thanks.